Right. Let's take a look at page 439. We're going to revisit limits today because I know it's been a while since we looked at those. Like those were the very first things that we talked about in this calculus course. But now that we know some concepts of calculus like derivatives and integrals, I want to show you how they can help us make these limit evaluations be a little bit easier. Okay, kind of a shortcut, if you will. So we're going to revisit limits, how we solved them the old way, like back at the beginning of the year. And then we're going to take a look at a shortcut way that we can use derivatives to our advantage to help us with those. Okay? But in the end, all of these are limits anyway. So do we remember what the first step is for a limit? What do you always try first? Yeah?
Plugging in the value.
Plugging in the value, whatever that x is approaching, okay? So let's try it for the first one. If you were to plug in -1 for all those x's, what would you get? Can we do that real quick? We get something undefined, specifically 0 over 0, right? An undefined value. That 0 over 0 is referred to as an indeterminate form. Okay, I think I referenced that vocabulary term at the beginning of the year. So 0 over 0 is an indeterminate form. Do we know what's happening graphically at that x location of -1? Do you remember what that 0 over 0 symbolizes? Yeah?
Vertical asymptote.
That's if we had a number over 0.
Oh wait, that's
0 over 0 is a whole, okay? So we know we have a whole at -1, that x value, but when we get done evaluating the limit, that's eventually going to tell us the height of that whole, like where exactly is that whole on a graph. Some other indeterminate forms are infinity over infinity, and perhaps we get an undefined value over another undefined value. So those are kind of our key ones to look for. If we do direct substitution forever and always, we'll try that first. If we get a number, that's awesome because that's the value of our limit. But if we don't get a number, it's most likely one of these indeterminate forms. How can we figure out the limit value if that was the case? Okay, so let's think about kind of old ways we did this at the beginning of the year. We now know direct substitution didn't work. We got 0 over 0. So how might you want to work around that issue? Is there some way we can manipulate that equation to our advantage? Change the way it looks? Yeah.
You could factor the top.
Okay.
And see if you can find something that cancels out.
Let's try it. So we can pull out a 2 from the top. Can we keep factoring? X squared minus 1 is a difference of perfect squares. So that would be x plus 1, x minus 1. Looks like the x plus 1s will cancel. So we're left with the 2 times x minus 1. So even though direct substitution didn't work at the very beginning, let's try direct substitution again now that we rewrote it. So if we were to plug in -1 for x, we get 2 times -2, which is -4. All right, so the height of that hole on the graph is -4. It's underneath the x-axis. We remember factoring from the beginning of the year? I hope. That's one tool we can use. Let's try B. If you were to plug in infinity for those x's, infinity squared is still infinity, times 3 is still infinity, minus 1, still infinity. Probably if we plug in infinity on the bottom, we would get an infinity as well. So notice how we get that other indeterminate form, infinity over infinity. How might we be able to analyze this one? We can't really factor in the same sense as we did the first one. Can we think about perhaps which value is larger? If we were to plug in infinity up top and plug in infinity down below? Or maybe think about growth rates, like what's growing faster, the top or the bottom? What do you think? Yeah.
Wouldn't they be kind of growing the same?
How do you know? Yep.
Because they're both x squared and the coefficients in the front really don't matter.
They do matter if they're the same growth rate. Okay, we're looking at the powers though. So they're both x squareds, okay? So we have the same growth rate. Okay, the top degree and the bottom degree are the same growth rate. But notice how the top is being multiplied by 3, whereas the bottom is being multiplied by 2. If they're growing at the same rate, the top is always going to be times 3 and the bottom is always going to be a times 2. We're going to be left with a 3 over 2, just those multipliers out front. We talked about at the beginning of the year, like if the top degree was larger than the bottom, what happened? If the bottom degree was larger, what happened? If they were the same degree, what happened? I hope those come back to us, okay? The same degree means we got to take the ratio of those coefficients. The +1, -1, or whatever on the end is kind of insignificant because if you're plugging in infinity, is subtracting 1 or adding 1 really changing the value at all? Do you see how those are kind of insignificant? Okay, so those really don't matter. We're just looking for those growth rates, aka the powers or the exponents. Which ones are larger? Bless you. Let's try the next one. Plug in 7. Always our first step. If we get a number, we're good. If we don't get a number, we might have to do some rearranging. What do you get if you plug in 7? 0 over 0. All right, indeterminate form. So at the beginning of the year, how did we get around that issue when we were working with a square root? Major brownie points if you can remember this. I know it's been a while. Yeah?
Didn't we like multiply it by the square root?
Close. The square root of x plus 2 and then? Plus 3. Do we remember what that's called? It's a conjugate. Okay, conjugate, it's where you keep the terms the same, but you switch the operation in between them. So if we're going to multiply by the conjugate up top, we're going to have to multiply by that conjugate in the bottom. All right, let's see what happens there. So up top, we're going to do a little FOIL, first, outside, inside, last. Square root times square root are the same, so they're going to go away. We're left with x plus 2. Notice how the outsides would be a 3 square root, and then the insides would be a -3 and then square root. So those would cancel. That's nice. And the last, we'd have -3 times 3 would be a -9. On the bottom, though, let's leave it as an x minus 7 times the conjugate, because the square root's not going to go away as nicely as it did in the numerator. Do you notice anything that's going to happen? Yeah?
But you're still going to have a 0 on the bottom.
Are we? What is x plus 2 minus 9? X minus 7 if you simplify it, right? And don't we have an x minus 7 in the bottom? Right. So there, that's going to go away. Much like the factoring, how we were able to cancel something out. So we're left with 1 over the square root of x plus 2 plus 3. So now that we rewrote it, we canceled something out. Maybe we removed or got rid of that issue that we had because of that, or for that indeterminate form. Let's try direct substitution again. If we plug in 7, we get 1 over 6. Perfect. So graphically, we know we have a hole at 7, and the height of that hole is 1/6. Okay, we could plot that if we wanted to. All right. So I hope those come back. But notice how, at least for the first and third one we did, it can be kind of tedious because you have some algebra work to do, either factoring or a conjugate. We're going to talk about L'Hopital's rule, okay? I think about it as L'Hospital without the S. But L'Hopital was a French mathematician, and he is the person that kind of generalized this relationship between limits and derivatives. I think we're really going to like this, okay? Let's say we have a limit, and it specifically has to be a fraction, okay? So you have some numerator stuff and some denominator stuff. L'Hopital's rule only works for fractions. If you were to try direct substitution, okay, always plugging in that number first, let's say we got 0 over 0, infinity over infinity, or undefined over undefined. Okay, if we get one of those indeterminate forms, this is what L'Hopital realized. Okay, he tried to find an easier way to solve limits instead of using like factoring and conjugates and growth rates, trying to remember those. Okay, he noticed the shortcut. What we're going to do is simply take the derivative of the top and the derivative of the bottom. Okay, this is not the quotient rule. We're not doing low d high minus high d low. Okay, L'Hopital's rule is simply the derivative of the top over the derivative of the bottom, and then we're going to substitute in that x equals a value to get our limit. I think we're really going to like this because it's taking derivatives, something we've been doing basically all year. Okay, so we're going to revisit the 3 at the top that we just did because we know what those limit values are. Let's see if we can get the same results using L'Hopital's rule. Okay, so here's that first one that we factored. We already said if we plugged in -1, we got 0 over 0. All right, let's try L'Hopital's rule. What is the derivative of the top? That's 4x, right? The derivative of the bottom? 1. If you try substitution again, okay, we're going to substitute in that value we're approaching, which is -1. What do we get? -4. Is that not the same limit value that we did by factoring? Old school, right? From the beginning of the year. But now that we are familiar with derivatives, we can use L'Hopital's rule. We couldn't do that at the beginning of the year because we had no idea what a derivative was. But now we do. All right, let's try B. If you tried direct substitution, you would get an infinity over infinity. Maybe you forget the growth rate rules. Okay, not the end of the world. Infinity over infinity is an indeterminate form, so we can use L'Hopital's rule. What's the derivative of the top? 6x. What's the derivative of the bottom? 4x. Okay, we're going to try substitution again. If you plug in infinity, 6 times infinity is still infinity. 4 times infinity is still infinity, right? It's still infinity over infinity. So L'Hopital's rule didn't really work, okay, at least doing it once. What if we were to do L'Hopital's rule again? Because we still got an indeterminate form. What's the derivative of 6x? 6. What's the derivative of 4x? 4. What does 6 over 4 simplify to? 3 over 2. That's the same answer we got from above, right? So you're going to keep finding a derivative and plugging in that number to test it. Okay? If you keep getting 0 over 0 or infinity over infinity, you just keep taking derivatives until you get a numbered value. Okay? I don't really know how many times you might have to take a derivative. That one we had to do it twice. The other one we only had to do it once. But L'Hopital's rule is pretty simple. We're just taking the derivative of the top over the derivative of the bottom and testing it after every single time we do that. Let's try the next one. We already said if we plug in 7, we'll get 0 over 0. That's an indeterminate form. So let's try L'Hopital's rule. If we take the derivative of the top, how might you want to do that? It's going to be a chain, yep. Let's maybe rewrite the square root as a power of a half. So chain rule, we'll bring down the 1/2, keep the inside. New power would be negative a half times the derivative of the inside would be 1. So no need to write times 1. But we then have to subtract the derivative of 3, because that's still a part of the numerator, but that's just going to be 0 anyway. Right, so there's the derivative of the top. What about the derivative of the bottom? 1. All right, let's go ahead and plug in 7. So we're going to have 1/2. 7 plus 2 is 9. All right. The square root of 9 is 3, but notice how the 1/2 power was negative, so that means we have to reciprocate the 3. Negative powers, you flip where it's located in the fraction. So 1/2 times 1/3, we get 1/6. That's the same as the top, right? Okay, so maybe you forgot to use a conjugate, or how that worked. Okay, L'Hopital's rule is a way to use derivatives to get around that. How are we doing so far? Pretty simple? Just taking a derivative? I think we can do that. All right, let's try some ones that we don't know the answers to. Okay, those other 3, we knew what to expect. Let's try the next one. Direct substitution, always your first bet. If you plug in 0, what's going to happen? E to the 0 is 1. 1 minus 1 is 0. Plug in 0 down below, we get 0 again. So notice how we have that indeterminate form. Let's go ahead and check out L'Hopital's rule. So derivative of the top over derivative of the bottom. What's the derivative of e to the 3x? Remember our derivative shortcuts? There we go. 3e to the 3x. And that's it for the derivative of the top. The derivative of the bottom is 1. So let's try direct substitution. We either A, get a number and we're good to go, or B, we get another indeterminate form and we have to do another derivative. Okay, we'll check it again. If we plug in 0, what are we left with? 3. There's the value of our limit. Now see, that one was nice because the initial function, we could not factor that like we did at the beginning of the year. That's not a square root, so we can't really use a conjugate. And since we're approaching 0 and not infinity, we don't have to analyze growth rates. So at the beginning of the year, this one would have been very difficult for us to do by hand. But now that we know derivatives, okay, we can get around that issue by using L'Hopital's rule. Let's try B. If we plug in 0, we're going to get 0 over 0. So let's do derivative of top over derivative of bottom. Let's see, maybe you want to rewrite the square root as a power of a half. Using our chain rule, we'll have 1/2, 1 plus x, new power is negative a half, times the derivative of the inside, but that's going to be 1 anyway. What about the derivative of the bottom? We just have 1. All right, let's plug in 0. So we'll have 1/2 times 1 to the negative 1/2 power. 1 to any power is just 1. So looks like we're left with a half. We hanging in there? All right, let's try the next one. We'll throw in some trig. This is supposed to be pi over 2, by the way. All right, so let's try direct substitution. secant of pi over 2. So we're at the very top of our unit circle. What do you think?
That would be 1 over cosine pi over 2, and pi over 2 is 0.
0. Okay, so secant's the reciprocal of cosine. Awesome. Cosine at pi over 2 is 0. So the reciprocal of 0 is 1 over 0. Notice how that's an undefined value. Let's check out the bottom. Yeah.
If you were to plug pi over 2 into tangent, tangent is sine over cosine, which does the same exact thing. Cosine would be 0, that would be undefined.
This is undefined as well. All right, so there's a difference here. Notice how if we have undefined over undefined, that is an indeterminate result, okay, an indeterminate form. If we had undefined over 1, okay, then the limit result would just be undefined, okay? We can't really calculate it to that extent. So we have to be careful about what we're left with. The only way you can use L'Hopital's rule is one of these 3 indeterminate forms. It has to take those shapes or those forms. So let's try L'Hopital's rule. We need derivative of top over derivative of bottom. So these are kind of throwback trig derivatives. I understand if we're a little rusty with those. What's the derivative of secant? Yeah.
I believe tan times secant.
Yes. Okay, so tangent x, awesome. Secant x. All right. And then we need the derivative of the bottom. The derivative of 1 is 0. We know that. Derivative of tangent, though.
Secant squared.
Secant squared. All right. So at first glance, L'Hopital's rule seems a little bit complicated because we have all these different trig functions. Maybe we can clean it up a bit. Notice how we have 1 secant function up top and 2 down below. So we could possibly cancel a set or pair of those out. We're left with tangent over secant. But maybe we can keep simplifying that. Is there some way we can rewrite tangent and secant? Maybe in terms of sine and cosine, because we're a little bit more familiar with those. Yeah.
Tangent you can write as sine over cosine. And since secant is just 1 over sine, you can just multiply the thing by cosine.
Okay, so if we were to write this out, we'd have this tangent function, sine over cosine, divided by 1 over cosine. Okay, that would be secant. Instead of dividing by a fraction, we can bring it up and multiply by the reciprocal, which would be cosine over 1. Notice how the cosines would cancel, so we're just left with sine of x over 1, but that's just sine of x. So let's try direct substitution. Okay, after every round of L'Hopital, okay, taking the derivative, we're going to test it. If we were to plug in pi over 2, sine of pi over 2 at the very, very top, I think Dan before said that was 1. All right, so there's our limit value. Even though it initially was undefined over undefined, we worked around that, taking some derivatives, and we figured out the limit. All right, let's try the last one. This one's an infinity. Natural log of infinity, going to be some infinity value. 2 times the square root of infinity, still infinity. Do we remember what grows faster, a natural log function or a square root function? Probably not. Okay, we talked about growth rates at the beginning of the year, but I understand if we lost some of those. So this is when L'Hopital is pretty useful. Let's take the derivative of the top. What's the derivative of natural log?
1 over x.
1 over x, good. And then on the bottom, we need the derivative of 2 square root of x. Yeah?
X to the power of -1/2.
There we go. All right, so there's L'Hopital's rule. Let's clean it up to see what we get if we were to plug in infinity. Maybe we'll rewrite this. We have 1 over x divided by 1 over x to the 1/2. Maybe we'll move it down and make it a positive power. But very similarly to the trig one, okay, instead of dividing by a fraction, we can move it up and multiply by the reciprocal. which would be x to the 1/2 over 1. Yeah? You want to keep going?
You end up with a square root of x over x, which now we can tell that the x would grow faster than the square root of x, and we can realize that that is close to 0.
There we go. All right, so take a look at this. The numerators will have 1 times an x to the 1/2. The denominators an x times a 1. Okay, so here's what we're left with. Now you could possibly analyze the growth rates. The growth rate of the bottom is 1, that's the power. The growth rate at the top is a 1/2. If the bottom is growing faster, aka getting larger than the top, you're going to have something small over something huge, which as the numbers get larger, that's getting closer and closer to infinity. Or sorry, closer to 0, my bad. So in the end, we're going to be left with 0 there. So even though we might not be able to analyze the growth rates of the original functions, like natural log and the square root, we can change it into easier growth rates, perhaps for us to analyze. Okay? How are we doing so far? Are we doing okay? All right, save the best one for last. First step of a limit, forever and always, is to plug it in. If we plug in 1 for x, what's the integral from 1 to 1? 0. If we plug in 1 down below, we get 0. That is an indeterminate form. So we can use L'Hopital's rule to help us figure out the limit. That means taking the derivative of the top and dividing it by the derivative of the bottom. Let's take a look at the top. How do you take the derivative of an integral? This was our second fundamental theorem of calculus. The derivative of an integral. Yeah?
F of the top times the derivative of the top minus f of the bottom times the derivative.
There we go. There's no need to work backwards because you're already taking the derivative of an integral. Those are inverse operations. They cancel each other out. So it's simply the top minus bottom idea, but we got to take the derivative of those bounds. I hope that sounds familiar. We did that at the beginning of this unit. If we plug in the top bound, that'd be cosine of x times the derivative of the top bound, which would just be 1. And then we'd have to subtract, plugging in the bottom bound, but then we'd have to multiply by the derivative of the bottom bound. And the derivative of 1 is just 0. So we know that's going to go away. Looks like we're just left with cosine of x for the top. What about the derivative of the bottom? We get 2x, okay? So let's test L'Hopital's rule. We're going to try direct substitution. If we plug in 1, we'll have cosine of 1. And in the bottom, we'll have 2. I have no idea what cosine of 1 is, because that's not a radian on the unit circle. So we'll just leave it like that. Notice how we get a number. Okay, it's no longer 0 over 0, or infinity over infinity, or undefined over undefined. All right. That's it for L'Hopital's rule. Is it a pretty simple concept for us? I thought it wouldn't take us that long to do it. Okay, so we have plenty of time left, like 10-ish, 15-ish minutes. Maybe you want to go ahead and try some of the homework ones, okay? These are multiple choice questions I've thrown in because we're starting to get close to the AP test. I think it would be a good idea to practice some of these. So they might go a little quicker because there's options, you know, which one it should be A, B, C, D, or E. All right? Do we want to try any of them together, or do you want to give them a shot on your own? Test to see if you know L'Hopital's rule. How about you try a few, and then we'll go over them if you have some questions, okay?